Recording in progress.
Yeah, comes on everyone. Let's start off. Yeah, let's start off. So last thing that we did was the non-standard Bose model. Did we do this? We did force one. Okay, let's do one more before going ahead. Potential energy between nucleus and electron is given by U is equal to U naught ln R by R naught. U naught, R naught are constants. R is the distance from center. Assume both series valid. Find the radius and velocity of the nth orbit. Right, I'll give you a minute. Let's see. I told you there are only two things that you have that you can use. One is your angular momentum is quantized, and second thing, F is equal to the centrifugal force. So how do we get force from potential energy? There is only one formula, F is equal to minus du by dr. And that will be minus u naught by r. Minus n indicates force of attraction. So we have u naught by r, force F is equal to mv square by r. V is equal to root over e naught by m, independent of n. Matlab, it doesn't matter which orbit you go, they'll all have same speed. And then we have my is equal to nh by 2 pi. Take this v, substitute here, you'll get radius, which will be nh by 2 pi mv, which is root e naught by m. Proportional to n. You know where you get these kind of fields? Infinite line charge. If you take an infinite line charge, then the field is 2k lambda by r. Clear with this? So you need to get the force that will be equal to the centrifugal force, and your angular momentum is quantized. These are the two things you play around with. Let's see one more. This is another important model. Let's see how you handle this. These are the kind of things I was talking. Like, you know, you will hear and you'll feel like, what the hell? But they'll be good advanced paragraphs. Think, read. Take 2-3 minutes, understand what the hell is he talking, and then let's see if you can figure out bits and pieces of it. What is he talking about? See, he's saying consider a one-dimensional box of Seisel. If you remember, I told you this, that MVR is equal to NH by 2 pi. When you rearrange the terms, you end up with, you know, that H by MV, the de Broglie wavelength is equal to N lambda. So I told you it forms a stationary waves in a circular thing, and that's what we call them, stationary orbits. So based on that, they made up an hypothetical theory. So let's say we got a box of length L. So here there are 4 electrons, ground state. Assume that the electrons are non-interacting, obey Pauli exclusion principle. We will see. Assume they're not interacting. Obey Pauli exclusion principle. I have no idea what the hell they're talking about. and are described by standing de Broglie waves confined with the box. This is the word that hits me first. Because I remember, right, that we talked about something called standing waves in, Bohr's theory. So this is how you get ideas in the exam. This is how you should think, like, in this, what word is hitting you? So are described by standing de Broglie waves confined within the box. So that means you need to think, so these electrons are having a de Broglie wavelength and these things are confined in the box and these are standing waves. So if you look at the first possibility, it is one harmonic. So this is your n is equal to 1. Second harmonic, n is equal to 2. Third harmonic is n is equal to 3. So somehow the electrons are forming standing waves. Like this. So basically the harmonics are your orbits. And he's saying the length of the box is L. So from here we can clearly see the length L must be an integral multiple of lambda by 2. Because length of one loop is lambda by 2, there can be n loops, where n is the nth harmonic or the nth orbit in this case. So from here we got lambda is equal to 2L by n. Remember, this is your de Broglie wavelength. And de Broglie is nothing but h by root over 2 times mass into kinetic energy. So from here we get kinetic energy will be h square by 4L square n square 2m, or n square into h square by 8m L square. And he has given, now now it is making sense. So this alpha white is given, so that for this. So this kinetic energy is nothing but alpha into n square. And since he said, there is one more word now I saw. He said these are non-interacting, meaning potential energy is 0. Therefore, the total energy must be potential plus kinetic. So the total energy must be alpha n square. This is the energy of the nth orbit. Making sense. Now he has given some options. Now he said there are 4 electrons and Pauli exclusion principle. Now it tells you something like, basically in one orbit, think about this logically. This is created by de Broglie wavelength of one electron. That means in one loop or one orbit, you can have only one electron. So there'll be one electron here filled. You have one electron here filled, one electron here filled, and one electron here. So the electron will be occupying n is equal to 1, n is equal to 2, and one occupancy in n is equal to 3. This is how the 4 electrons will occupy. Now have a look at this question. Now it will make sense. If you have encountered something similar to this, even if they play with this in different ways, you can still play around. Have a look at this. Any doubts on this? The idea is important. If you see in this chapter, right, we did some weird things already like this. One was the non-standard Bohr's model, right? And this one, the photons firing and everything, the recoil speed. Another thing was what? Non-standard Bohr's model, this one, this Bohr's theory. We have next one, we have one more after this. Okay with this. Now, let's see the options. E naught is what? So initially, if I take the box, electron, electron, and electron. So this is the initial energy state. So E naught. This is the ground state. That will be alpha into 1 square, alpha into 2 square, plus alpha into 2 square, plus alpha into 3 square. That will be 9, 1, 10, 4, 4, 18 alpha. That is your E naught. First option is wrong. The energy of the highest occupied state. Here the highest occupied state is the n is equal to 3. So energy for the third state will be alpha into 3 square. 9 alpha. That is also not matching. the total energy of the first excited state. In this, can you tell me, when you say first excited state, which electron will jump where? And next question is second excited state. So looking at this picture, can you tell me what is the first excited state and what is the second excited state here? Think, take a minute. Suppose if we have an atom like this and the electrons have to jump to next excited state, how will the electrons jump? Which case will take more energy? 1 to 3 jump or 2 to 3 jump? Or which case will take least energy? 1 to 3 jump or 2 to 3 jump? 2 to 3 jump, isn't it? So the first excited state, and ऊपर से jumping from 1 to 3 directly, right? Will there be also shielding effect and everything? But anyway, we always see in terms of energy. So the minimum energy required for the transition is from 2 to 3. So the first excited state, you have an electron here, we have an electron here, we have an electron here, and we have an electron here. Electron jumped from here to here. This is your first excited state. So energy of the first excited state will be alpha plus alpha into 2 square, alpha into 3 square plus alpha into 3 square. That will be 9, 9, 18, 4, 23 alpha. What is the second excited state? Now, see, you have two possibilities, huh? The electron. So here the reason is energy from n is equal to 2 to n is equal to 3 is less than 1 to 3 transition. Now you tell me, again you have an option. The electron in the second orbit can go to the third orbit, or the electron in the first orbit can come to the second orbit or third orbit, isn't it? Which will take least energy? 1 to 2 transition or 2 to 3 transition? 1 to 2 transition, isn't it? So the second excited state, electron, electron. So this thing jumps from here to here, electron and electron. This is your second excited state, because 1 to 3 transition will be least energy compared to 2 to 3 transition. So you should understand that thing. The atoms will always try to excite in such a way the energy is as least as possible. So this configuration will have the least energy in the second excitation state. You could have gone from 2 to 3. Now understand one thing, these orbits are weird. Did you observe in these orbits, the higher you go, the energy is increasing higher and higher. In our regular orbits, it used to be 1 by n square. Here it is into n square. So the higher the orbit, the more energy difference is coming up. So the electrons will maximum try their best not to go as high as possible. So here again, same thing. Energy from n is equal to 2 to n is equal to 3 is greater than energy for the transition from n is equal to 1 to n is equal to 3. So 1 to 2 transition will happen here. Now what is energy for this system? Alpha into 2 square, alpha into 2 square, alpha into 3 square plus alpha into 3 square. 9, 9, 18, this will be 28 alpha. 28 alpha, I can write this thing as 9. This is how much here? This is 9, 4, 4, 18. Na? 4, 4, 8, 8 and 9. 26, na? Wait, how much is this? 26 alpha. Did I mess up something here? 4, 4. So C option is what? E naught plus 9 alpha. That is 23 alpha. This will be 18 alpha plus 5 alpha. That will be E naught plus 5 alpha. This will be 20 E naught plus कितना था ये? So this can be written as 18 alpha plus how much is this? 8 alpha. What am I thinking? This is E naught plus 8 alpha. D option. And that is only option matches. It's a single choice question though. Have a look at this. You can make this into a paragraph. You can play around a lot. Clear with this. There. So that is how they can mix up your de Broglie wavelength with standing waves and Bohr's theory. And you will encounter something of this sort in some exam. Maybe some practice test or some advanced way or somewhere. So then you should know how to handle these things. Mostly the terminology. You need to get an idea that you can create the standing waves. And if you remember, I told you this in Bohr's theory, but there, 2 pi r is equal to ns by lambda, they form stationary waves and energy in a stationary wave is constant. So that one statement you need to realize, boss, I can use this for even for 1 day. Clear with this? There, once you understand, it actually looks fine, but yeah. Let's see one more. The next thing, this is also important things, atomic collisions. Now, when we studied in collisions, right, when we say two bodies collide and they lose energy, and we say, how do they lose energy? They become heat and, deformation and sound and everything. Fair enough. But when atoms collide and lose energy, now you can't say it becomes heat. If you think about it, what is heat? Heat is nothing but molecular kinetic energy. The kinetic energy of the molecules is only called heat. So when molecules collide and the energy lost cannot become heat, there is no sense only. So where does this energy go exactly? So whenever the molecules collide, the energy lost is actually used to excite the electrons to higher orbits. And when they de-excite emitting photons, that is the reason when you heat up a gas, it starts emitting and it becomes bright. So unlike large bodies, this molecules and atoms, they don't have an option. If you lose energy, that energy has to go for de-excitation of electrons because there is no one else who can take the energy. There is no meaning of deformation of an atom, isn't it? The nucleus is there, electron is there. What do you mean by deformation? The electron, instead of going like this, will start going like this. What? It got deformed. The orbit got deformed. It doesn't make sense, right? So there is nothing called deformation energy or heat energy for molecules as such. So then there's only one place you can lose energy. So let me explain this with an example that will be better. Let's say we have a hydrogen molecule going with speed v, and there's one more hydrogen molecule at rest. And let's say this is a head-on collision. So if both the molecules collide perfectly inelastic, they stick together and they form a H2 molecule. Consider a hydrogen atom. colliding with another hydrogen atom at rest. So let's see how do you solve these kind of problems. The first thing, you start with an assumption, assume perfectly inelastic collision. Because that is the worst thing that can happen, in which you can get a maximum loss of energy. This is going with speed v, this is at rest. After collision, they stick together. They stick together, that's your perfectly inelastic collision. This is how you get a H2 molecule. We see the speed becomes v by 2, conservation of linear momentum. So in this scenario, we get a maximum loss of energy, which will be half mv square minus half 2m v by 2 whole square. This turns out to be mv square by 4. Now here, if you observe, the each hydrogen atom takes mv square by 8. Because both the hydrogen atoms, there is a symmetry, we can say each hydrogen atom will take half of that energy. Till here, it is standard stuff. Now, something interesting happens. Now, this atoms, right, we have a problem. If you remember, these electrons, they are very, what you call, specific. They take only specific amounts of energy. They are like very picky eaters, like actually. They will not eat anything that you give. They want only specific amount of energy. You give anything more or anything less, they are least bothered. So case one, if mv square by 8 is less than 10.2 ev, then what will the electron say? Boss, this is not sufficient for 1 to 2 transition. Therefore, electron will not take this. Means you cannot lose any energy. If you cannot lose any energy, what kind of collision is this? This is not sufficient for n to 1 to 2 transition. Therefore, there is a no loss of energy. If there's no loss of energy, that means the collision is perfectly elastic. That means this is what will happen. The hydrogen atom which is coming with speed v will collide with this, which is at rest. After collision, since both are identical, this will come to rest and this will go with speed v. Basically, this is bounce off. H2 molecule does not form. That means if you take nitrogen gas and hydrogen gas and put them in a room, and if you just put a regular temperature, no matter how long you wait, ammonia will never form. That's why if you see in chemistry, right, whenever you see reactions, they mention the temperature on the reactions. Temperature becomes a very important factor for a reaction to proceed. If you don't have enough temperature, no matter how long you wait, the product will never form. And that too for a molecule like ammonia, NH3, 3 hydrogens have to collide and stick. The probability becomes pretty low. And so the formation of ammonia will be negligible. So you need to give sufficient temperature. Second case. If mv square by 8 is exactly 10.2 ev. Again, remember this is the maximum possible loss. You can lose this much. Now you have two options. Lose exactly 10.2 ev, then they will stick. Or don't lose any energy. You can't lose anything less than this, or you can't lose more than this in this case. They will bounce off. Again, remember, here I've taken a very special case, which is a head-on. It can be even oblique collision. Na? So this thing will form H2 molecule. This will bounce off. And how do you give kinetic energy for the molecules? 3 by 2 kT, thermal kinetic energy. Increase the temperature, the kinetic energy increases. So by heating up the gas, you can actually increase the temperature. If mv square by 8 is, let's say, 12.1 eV, now we have three possibilities. We can lose exactly 12.1 eV, we can lose 10.2 eV, or we can lose nothing. Now we have three possibilities. Now we can see what is happening. Just like, the orbitals are quantized, the energy lost is also quantized, meaning there is a certain factor. Like you can lose only this much. So you have certain values now. So this will be perfectly inelastic. Where Ega value is 0. This is inelastic. Ega value will be less than 1 and 0. This is perfectly elastic. E is equal to 1. E is the coefficient of restitution. Now you can keep going doing this. If you have case 4, where if mv square by 8 is greater than 13.6 eV, and now the electron can go to any orbit or escape to infinity. Favor this? So this is how atomic collisions work. So when molecules collide, they cannot lose whatever energy they have. They have restrictions. So you get cases, possibilities. Now, just to solve this a little faster, if you just want to find the maximum loss of energy, if you have a mass of m1 going with v1, mass of m2 going with v2, after collision they will stick. They'll go with v common. So max loss of energy is given by half mu v relative square. Mu is your reduced mass and v relative is. This we saw in momentum, center of mass momentum and collision chapter. I taught you a trick there. There, page 115. If you have two blocks of mass m1, m2, spring constant K, speed is u1, u2. Find the maximum compression. So the change in kinetic energy of the system becomes the spring energy, which is half mu v relative square. Yeah, you can always just conserve momentum and write the energy and everything. I'm just showing you. So refer this, but quite a good result. Saves you time in the exam. Page 115, center of mass. Let's see a question based on this. Let's say we have a neutron. Is going with speed v. Collides head-on with a helium He plus molecule. So there's only one electron there. This is a head-on collision. Mass of helium is 4 times the mass of neutron. find the minimum speed so that the electron will transition to nth orbit. Let's see how will you handle this. The previous example I gave you for hydrogen and hydrogen, I'm giving you neutron and helium. So how do we start? Think a little minute more. Let's see. Something like that, right? So what is the maximum loss of energy? Half mu v relative square. That will be half into m1 m2, that is 4m by 5. V relative square is v square. This will be 2m v square by 5. Now all this energy will be taken only by the helium. Why? If neutron takes the energy, what will it do with it? Does neutron have electrons? Neutron does not have electrons, so it cannot take any energy. So the only one who can take all the energy is helium. Since neutron does not have any electrons, it cannot take the energy. What will it do with it? Suppose if this had been hydrogen and helium, then there would be a confusion. How much hydrogen will get, how much helium will get. That you can't guess actually. They have to give you some information about it. So you can't say they will divide in the ratio of mass or equal. Neutron does not have electrons. Therefore, all energy is taken by helium. Then you're done basically. So this maximum energy, which is 2mv square by 5, must be used for exciting an electron. That will be 13.6 eV into 1 by 1 square by 1 by n square into z square. Z is 2 here. So you will get, this will be your minimum speed required for the nth orbit. So that will be how much? 27.2 eV into 5, 1 minus 1 by n square ka root. This is your minimum speed for an nth orbit. They can ask you find the minimum speed for the to emit a photon. So then you take n is equal to 2. 1 to 2 will take the least energy. There is a mass term also. Clear with this? Next thing. So it's really not that tough. You just need to realize the loss in energy will become the difference in energy between two orbits. Next one. Similar one, but let's say we got a neutron going with speed v. The kinetic energy of the neutron is 65 eV. We have a helium molecule, mass is 4m at rest. This is the picture before collision. After collision, this is the line of collision. The neutron went away perpendicular to the line of collision, and the helium molecule, it started going like this at some angle theta. It's an oblique collision. They flew off at angles. This is the picture after collision. We don't know v1, v2, we don't know theta. I'm just giving that. We don't know any of those velocities. v1, v2, theta are unknown. A neutron collides with a He plus obliquely. Scatters at 90 degrees after collision as shown. Find the possible values of kinetic energy of neutron. So after a collision, what can be the values of neutron ka kinetic energy? And frequency of the photons emitted. Or energy of the photons emitted. So after this collision, how many different photons can come? And what is the energy of the nitrogen after collision? So I hope you remember this. Energy of the first orbit for helium will be 54.4 eV. Second orbit will be minus 13.6 eV. You can calculate this, the 13.6 into z square. Minus 6.60 eV. D4 will be minus 3.4 eV. Let's see how will you approach this. This is what I was telling you. The concepts will look similar to chemistry, not the questions. Think how will you handle this. How do we start? Let's do one thing. You would have taken as velocity v, na? So can you conserve momentum in the horizontal direction and the vertical direction? You can conserve linear momentum. Try to eliminate that theta. So get me a relation between v, v1 and v2. Eliminate theta. Try that. It's like I said, it's more of a collision problem. Conserve momentum and then get the energy from there. Let's see. Right, Advait. So from there, how will you proceed? So we have the neutron going with speed v. So we have the helium, which is at rest. After collision, this guy has gone to v1, and this guy has gone. I'll do one thing. I'll just write it as masses, m and 4m. So, and remember here, this thing is u. So half m u square is 65 eV. This is given. Conservation of momentum. So initial momentum will be mu is equal to 4m v2 cos theta. Vertical momentum mv1 must be equal to 4m v2 sine theta. There, square it on both sides. You'll end up with u square plus v1 square is equal to 16 v2 square. There, you eliminated theta from there. Now, what is the loss of energy? Loss of kinetic energy will be half mu square minus half mv1 square plus half 4mv2 square. Take this thing and dump it in this. Now this loss in kinetic energy becomes a photon, right? This would be half mu square minus half m v1 square minus 2m v2 square will be u square plus v1 square by 16. That will be half minus 1 by 8. That will be 3 by 8. Half plus 1 by 8 will be 5 by 8 mv1 square. Now, why am I bothered about v1 and not v2? Because in the question, if you remember, they asked kinetic energy of the neutron, which is half mv1 square. This is your loss of kinetic energy. So this energy must have gone into the excitation of the electrons. Any doubt still here? This is pure mechanics. I didn't use anything related to modern physics yet. Now comes. So this loss in energy, let me just modify this. 3/4 half mu square minus 5/4 half mv1 square. So I can write this thing as 3/4 into this is 65 eV. This is minus 5/4 kinetic energy of the neutron. This energy must have been absorbed in the form of a photon. So that would be 13.6 eV into 1/1 square by 1/n square into z square. So from here we get, this is 3/4 into 65 minus 54.4 1/1 minus n square. This whole thing of 4/5 is kinetic energy of the neutron. You just have to solve a bit. How much is this? 65 into 3, that is 195/4. 4's a 3/5. I'll just make it 196. So then it'll become easy. That'll become 49 then. 196, it'll become 49 minus 54.4 plus 54.y by n square. This is your kinetic energy of the neutron, which will depend on that n square is your the next orbit where you're jumping. Remember, this value should be always greater than equal to 0. Na? You cannot have kinetic energy negative. Kinetic energy of the neutron is always greater than equal to 0. That 4/5 goes off. Then you end up with 54.4 by n square is greater than equal to, how much is this? 54.4 minus 9, that's around 5.4. Then we get n square must be less than equal to 544 by 54 ka root. When you look at this, that thing looks close to 10. So root 10 is again, so approximately I'll just put around 3.1 something. Anyway, we have to take the nearest integer. That means you cannot exceed n is equal to third orbit, isn't it? You don't have enough energy to excite electrons to fourth orbit. So this implies electrons, we do not have enough energy you can actually check for each orbit also. We do not have enough energy for n is equal to 1 to n is equal to 4 transition. Therefore, the acceptable values of n are n is 1, 2, or 3. Clear with this? So if you put 1, 2, 3, I'll get different values of kinetic energy. So those are all the possible values of kinetic energy. And what about the photons? So if you go from 1, 2, 3, then therefore the number of photons will be, so we get 3 different photons. We can get a photon from 3 to 1 transition. We can get a photon from 3 to 2 transition. We can get a photon from 2 to 1 transition. If you excite to the third orbit, you can go from 3 to 2, 3 to 1, or 2 to 1. Clear with this? That's how your advanced paragraph will look like. Atomic collisions. So there you saw in Bohr's theory, we had the non-standard Bohr's model. We had atomic collisions, head-on and oblique, and then we had that standing waves wala thing. These are the 3 different models. These are generally not asked at mains level, but advanced method you can expect. This is how they'll trim paragraphs, which will look completely weird, like what the hell is he talking about? But if you actually read carefully and observe, you will see there's a lot of mechanics involved. Check out the steps. The main thing is this: if you got this, your job's done actually. So the loss in energy must go somewhere. It is used to excite the electrons. So this loss of energy must be equal to the energy transition between 1 to nth orbit. So that will give you a limiting value of kinetic energy of the neutron. Play with this. So that's your Bohr's theory. Like I said, Bohr's theory and photoelectric effect are the bigger ones. The next thing, X-rays. So let's see. This is boring X-rays ka theory. This is more theoretical. So what are X-rays? X-rays are simply the electromagnetic waves in the wavelength range of 0.1 to 100 angstroms. If you remember, 4000 to 7000 is the visible light. So 0.1 to 100 angstroms is the X-rays. 0.1 to 10 angstroms is called hard X-rays. Right? These are have more energy. Just think about it. If it even you take 1 angstrom, you know how much energy is that? 12400 by 1 angstrom, that is 12,400 EV or 12,400 volts. So you need to apply 12.4 volts, 12,400 volts to get a 1 angstrom X-ray. These things are very high energy. The 10 angstroms to 100 angstroms is a soft X-rays. These are used for the medical purposes. So when you go for an X-ray machine, you're actually getting hit by soft X-rays. Hard X-rays are used, when industries and all, you have a factory ka machine and there are cracks, 1 or 2, meters ka thick steel. So you use hard X-rays. X-rays are unaffected by electric and magnetic fields, obviously, because these are also electromagnetic waves, just like photons and everything, just like visible light. Except for the wavelength, there is no difference between this. So in this part, right, what we'll be dealing is primarily the production of X-rays, how X-rays are produced and the what kind of X-rays and all. So that is a main theme in this. It's a small part. So let's see. So the setup is called Coolidge tube. You should know the words, because in the exam they'll start the question like this: in a Coolidge tube, the voltage of the battery is doubled, and you have no clue what the hell is Coolidge tube. You might even think it's a refrigerator or something, because cool ka word is there, na? So you might think it'll cool something. People have done that. They have to be careful. So let's see the setup. Again, I'm just drawing a rough sketch. So here we have an emitter plate. And here we have a heater. So when you switch on the heater, the emitter plate gets hot and it starts emitting electrons. This is called thermionic emission. Then you connect this emitter plate to a battery, a high voltage battery. We give around 10 to 25,000 volts. Next time when you go to an X-ray machine, observe that it will be written danger high voltage karke. So you operate this around 10 to 20,000, 25,000 kV. It can be even higher. And here we have something called a target material. So this goes and gets connected to this. So that becomes positive charge and this becomes a negative charge. So electrons are accelerated to high voltages. These electrons gain really high speeds. Then they go and bombard with the target. When they bombard with the target, they start emitting X-rays. Now, why they emit, we will see that. So this target material, the triangle shape which I had drawn, is called target. So this is generally made of heavy metals like tungsten, and they can even use copper and all that stuff, but preferably they use tungsten, molybdenum. Something of that sort, the heavy metals. Now, when you're colliding this with a lot of electrons, because of collision, it gets heated up. So you have a coolant also. Maybe you're pumping water or some kind of thing. So you have to send a coolant in order to cool the target material, to cool the metal from overheating. So what are happening? First thing, the electrons are emitted by the emitter due to thermionic emission. If you remember, before the photoelectric effect, I explained you what is thermionic emission. Then these electrons are accelerated to high speeds due to the high voltage battery. And bombard the target material. And we observe X-rays. There are two ways you get X-rays in this. You will see both of them separately, but when you see a textbook or something, they will just give the everything together. Now the problem with this thing, when you're going and bombarding a target, you actually lose a lot of energy. Roughly only 0.1% of the energy is converted into X-rays. That means a lot of it becomes heat. The remaining energy becomes heat. And you might get other radiations also, like ultraviolet or visible light. But we are more keen on X-rays, so remaining everything is just wasted. So because of this, what will happen? The target gets heated up. So now you tell me, if it is going to get heated up, the target should be made of what kind of material? Should it have high conductivity or low conductivity? Should the target have high conductivity or low conductivity? When the coolant comes and goes over it, you want the heat to be removed fast or heat to be removed slowly? You want the heat to be removed fast, isn't it? So it should have high conductivity. Should you have high melting point or low melting point? Let's say you want it to melt at 300 degrees or 4000 degrees. You don't want to melt, so you need high melting point. You want to have high specific heat capacity or low specific heat capacity? What is specific heat capacity? Let me ask you this way. For a given amount of heat, do you want the temperature to rise fast or temperature to rise slowly? You want the temperature to rise slowly, so you need high specific heat capacity. Because if you have more specific heat capacity, that means it's more difficult to heat up the body. Clear with this? Then let's see how do you get this X-rays. Take a break, come back by 7. We'll continue after that because that thing will go in a stretch. Any doubt so far? Chalo, come back by 7. Shut up, everyone. So the first thing is continuous X-rays. Now, books and everything, right? You will see everything in one go. Let's split it. Now, if you remember, there's a statement in Rutherford model. According to classical theory of electromagnetism, an accelerating charged particle emits photons. Now, why this happens, we have no idea, but it happens. Others, keep your hands on. And if you see that was a drawback in the Rutherford model, then they argue since the electron is going in a circle, it has centripetal acceleration, therefore should keep on emitting photons and eventually collapse. That was a full statement here. So same thing will happen here. So if you take the nucleus, so the electrons which are coming from the emitter, some of them will just pass through. So let's say they enter with speed u, because the nucleus is attracting them, they will start deviating. They might bend and they might come out with speed v. Let's say u is greater than v. In this process, the energy, whatever is lost, comes out as a photon. So the difference in energy of this electron before entering and leaving, that difference becomes a photon. The electrons are deflected by the nucleus and come out with less energy. Because if you're deflecting, means you accelerated or decelerated. Now here, the fastest moving electron. So when do you get your maximum energetic photon? You get the strongest photon when your fastest moving electron collides and stops in one collision. If your fastest moving electron stops in one collision, all the kinetic energy becomes photon. So kinetic energy becomes hc by lambda minimum. So more energy, less wavelength. Kinetic energy is nothing but E into V. So E into voltage. Therefore, we get the formula. The minimum wavelength of an X-ray machine is given by hc by E into voltage. There, this is the first formula in X-rays. There are only two formulas in X-rays. So this is one of them. So this is the extreme case where your fastest moving electrons just stop in one collision and all that energy becomes a photon. So an X-ray machine cannot produce a wavelength less than this. It all depends on the voltage. The higher the voltage, the more energetic photons you get. And these are called continuous X-rays because each electron can lose any amount of energy. There is no restriction in that, isn't it? So that means you can generate all wavelengths of X-rays. That's why it is called a continuous X-rays. So if you try to plot a graph for this, again, remember, you will not see these graphs in the book because they'll always give the combined graph. if you try to plot a graph for intensity versus wavelength, it looks something like this. So this is your lambda minimum, this is your voltage V1. If I increase the voltage, then lambda will decrease, and you will also notice the intensity also increases. V3 is greater than V2 is greater than V1. Again, this is a graph only for continuous X-rays. So, okay, one thing is clear. If you increase the voltage, you get less wavelength. Fair enough. But why is the intensity increasing? So the thing is, lambda minimum by hc into E into voltage. So if you apply higher voltage, this implies higher kinetic energy of electrons. If you have higher kinetic energy, you will collide more before stopping. And if you have more collisions, you have more photons. If you have more photons, more intensity. So if you operate your X-ray machine at a higher voltage, it produces more X-rays than a lower voltage X-ray machine. Okay with this. It's like, think of like this, an arrow can, let's say, go through 3 cardboards with speed V. If you double the speed, it will go to more cardboards, isn't it? It will just keep colliding and pushing through. So this is one way you get X-rays because of that X-ray classical theory of electromagnetic thing. This is also called as breaking radiation or Bremsstrahlung radiation. There's a technical name for that. It's a German scientist name. This is one way. There is a second way of getting an X-rays. This is called characteristic X-rays. When the target is bombarded by electrons, some electrons are knocked out of their shells. Creating vacancies. Now, if you have a vacancy, the electrons in the higher orbit won't keep quiet, they de-excite. Emitting photons. So we have an electron sitting here. Comes here, this thing bounces off. This electron bounces off, something of this sort will happen. This creates a vacancy there. Now, if you have a vacancy in the first shell, now if you name the shells, we know it is a K shell, L shell, M shell. So if an electron jumps from L to M shell, this is called K alpha. See how to read this. K alpha, K meaning you're jumping to the K shell. Alpha means first possibility. So when you say K alpha X-ray, means it's an electron jumps from N is equal to 2 to 1. So you're jumping into the K shell, which is N is equal to 1. Alpha means first possibility. So you are jumping from 2 to 1. Suppose if you jump from 3 to 1. Again, you're jumping to the K shell. Second possibility, we call it K beta. You're getting how to read that? If I say K gamma, means you're jumping from 4 to 1 shell. Similarly, if there's a vacancy in the L shell, if you jump from here, this is L alpha. You're jumping to the L shell and the first possibility, L beta. So generally, these are the 4 X-rays you get. So K beta, electron jumps from n is equal to 3 to n is equal to 1. L alpha is n is equal to 3 to n is equal to 2 transition. L beta is n is equal to 4 to n is equal to 2 transition. That is, you can read them. Now, if you try to actually plot a graph for intensity versus wavelength, you will notice there are only 4 wavelengths, isn't it? We just got 4 lines here. K beta, K alpha, L beta, L alpha. We will talk about that. So if you see, we get only 4 specific wavelengths. So the reason it is called characteristic is because these wavelengths will depend on the atomic number, isn't it? Depending on the metal, you get different wavelengths. So if you actually try to figure that out, the difference in the energy orbits, En2 minus En1, delta E, which is Hc by lambda. So this is 1 by lambda characteristic. The Rydberg constant formula which we used. We have Rydberg constant by 1 by N1 square minus 1 by N2 square into Z effective square. We'll talk about that. So what is the Z effective? Z effective is Z minus sigma. Sigma is your screening constant. Think about it. When the electron is jumping from 2 to 1, in 1 there's already 1 electron sitting, isn't it? Shielding effect, basically. Screening constant or shielding effect or whatever you want to call it. So the electron which is jumping from 2 to 1 will think inside there are Z minus 1 protons. So there is a vacancy here. There is an electron here. So when this electron is jumping here, this electron will feel inside there is a Z minus 1 protons. So it gets repelled by that electron in the first orbit. So it feels Z has decreased. So here, if you observe few things, lambda characteristic, this is independent of voltage of the source. Obviously, it depends on the electronic transition. It doesn't depend on the voltage of the Coolidge tube. Lambda characteristic is independent of voltage. Depends only on the atomic number. And independent of voltage. Second thing is more like a precaution thing. We generally use, the target metal should have a high, the target should have a high atomic number. Should have a high Z. Else, there is a chance, think about it, if Z is small, then lambda also will be big, means your wavelength might not be in the range of X-rays. Else, there is a possibility the wavelength will be, there is a possibility wavelength will not be in X-ray region, it might be in ultraviolet or visible light. There is a possibility of lambda not being in X-ray range. Let's say if you use metal like something like sodium or copper, and if you don't give enough energy, instead of getting X-rays, you might get visible light and ultraviolet. Not being in X-ray wavelength range. Now, if I combine both the graphs, this is the actual graph which you will see. This is the graph you should remember. something of this sort. This is your lambda minimum. This is your lambda k beta. This is your lambda k alpha. This is lambda L beta. That is lambda L alpha. So the spikes here, so basically you're adding this graph, this straight lines here, plus this continuous graph, isn't it? So the spikes actually represent the characteristic spectrum. So when you add a continuous graph to the spikes, that straight lines, you get spikes. The spikes represent characteristic spectrum. Now, if you observe something here, tell me one thing, which photon will have more energy, K beta or K alpha? K beta is 3 to 1 transition and K alpha is 2 to 1 transition. So technically speaking, energy of K beta is greater than energy of a K alpha photon. So even though K beta has more energy, if you observe here, intensity of I alpha is more. K alpha is more. Shielding effect. Think about it. When you jump from 3 to 1, the electrons in the second orbit will repel the electron. So is it more easy for an electron to go from 2 to 1 or 3 to 1? 2 to 1 is more easy. The probability of 2 to 1 is actually much higher. Almost for every 100, K alpha photons, there's only one K beta photon. So that is the reason, even though your energy is less, you get a lot of photons, so the overall intensity increases. So that is a reason, shielding effect basically. It is easier for n is equal to 2 to n is equal to 1 transition. Compared to n is equal to 3 to n is equal to 1 transition due to shielding effect or screening effect. That's the reason K gamma, right? We will not even write also. It's pretty rare. A 4 to 1 transition. There is just too much shielding effect. Clear with this. These are the kind of theoreticals they'll ask you. Even though K beta has more energy for a photon, why does the intensity of K alpha is more? This is the graph you should remember, everyone. Check out the graph. Ask me if there's any confusion in this. So let's see how they'll frame questions based on the graph. Any doubts so far? There is a bit of a theory. Can't the rest of the chapters like this only. There is a lot of theory in this. So these things can be explained like a theory or question. So let's see. Either way, I'll keep all of them together. This is a very good question they can ask you. So let's say we have two different Coolidge tubes. This voltage is V1, atomic number is Z1. The second Coolidge tube, this is voltage V2, Z2. Compare V1, V2, Z1, Z2, which is bigger, which is smaller. This will be the question. We have two different X-ray machines with different voltages and different atomic numbers for the target. The graphs are plotted. Looking at these graphs, compare which voltage is greater, V1, V2, Z1, Z2. Voltage and the atomic number. Try. Take a minute, we'll think about it. Let's see. V1 greater than V2, Z1 greater than Z2. Okay, let's see. If you look at this is your lambda K alpha for this guy. If you look at this is the lambda K alpha for the green one. This is your lambda minimum, let's call it lambda 1, and this is your lambda minimum, which is lambda 2. Now be careful, there are two different lambdas here. One is a continuous spectrum, so lambda minimum belongs to the continuous spectrum. Lambda minimum is hc by E into voltage. So this is proportional to 1 by voltage. You can clearly see lambda 2 is greater than lambda 1. Therefore, you can see V1 is greater than V2. You can remember like this also. If you have a high voltage, you get more energy, so less wavelength, isn't it? So you can clearly see lambda 1 has more energetic photons compared to this thing. Great. The second one, the spikes are the characteristic spectrum. That formula is 1 by lambda characteristic. So be careful, don't mix up both the lambdas. This is given by R into 1 by N1 square minus 1 by N2 square into Z square. So you can clearly see 1 by lambda characteristic is proportional to Z square. So here you can clearly see now, again, look at the K alphas. The red ka K alpha is more energetic than green ka K alpha, less wavelength. So the lambda red is less than the lambda, the green one. So then the atomic number will be Z2 is greater than Z1. Is that making sense? We're talking about two different lambdas. A simple way to remember like this. If you can clearly see the green ka K alpha is weaker. See, what is K alpha? 2 to 1 ka jump. Agreed? In both the cases, you're jumping from 2 to 1. But for some reason, the red one has more energy than the green one. Means what? The atomic number is more, isn't it? Is that making sense? That is the only explanation. If both of you are jumping from 2 to 1, but one guy has more energy than the other guy, then the only difference must be the atomic number. Make sense? So without writing any equations, you can just argue and get the answer also. But with equation, that is how you get it. It's a pretty good question. This will be a pretty good mains level question. Any doubts on this? Let's see one more in this. So case 2. Let's say this is T1, this is T2. T is the temperature of the emitter plate. So you can change the temperature of the emitter. These things are never asked. So can you compare T1, T2, which is bigger? Who has more temperature? This is P1, this is P2. P is the pressure of gas in the chamber. We prefer to keep the cooling tube vacuum, but sometimes air does leak out. You can't do anything about it. So again, we have got for P1 and P2, pressure of the gas chamber. Which pressure is more? How will you compare these things? Both have same lambda minimum, matlab both have same voltage. So atomic numbers are also same. If you can see, I kept K alpha, K beta ka spikes at the same place. So the spikes will talk about the atomic number. The lambda minimum will talk about the voltage. So here we are playing with temperature and pressure. Take a minute. How will you think about this? Let's see. Think about it. If you increase the temperature of the emitter, what happens? If you have more temperature, if you heat up the emitter more, you get more electrons. If you get more electrons, these things will go and collide with the target. You'll have more collisions. If you have more collisions, you will get more photons. That means more intensity. So this is one way to increase intensity by just increasing the temperature of the emitter plate. You can clearly see T1 intensity is more than T2, so T1 is greater than T2. How does pressure of the gas in the chamber affect? Now, if you look at the pressure in the gas, the chamber ka volume is constant. So the pressure P is proportional to the number of air molecules. Now, if you have more air molecules, remember electron cloud? These electrons which are coming from the emitter, they start colliding with these air molecules and they start forming electron clouds. And these things will start blocking the electrons, so the collisions will decrease. Due to the collision of electrons. So that is the reason we prefer to keep it vacuum. Generally, they maintain a low pressure with the air molecules, creating electron clouds. We heard this word in photoelectric effect, which opposes the incoming electrons. So more pressure, less collisions, therefore less intensity. So if you have more pressure, then intensity will be less. So who has more intensity? P1. So P1 must be less than P2. Clear with this? The one with the least pressure will have more intensity. Got this? Or let me write it as P2 greater than P1, same thing. The graphs are important. They can play around with the graphs. The second formula in X-rays is Moseley's law. This is mostly an experimental thing. This is only for characteristic X-rays. So this person Moseley, right? He checked out all the data and based on that, he formulated a formula. The formula is important. Root over frequency is given by A into Z minus B. I'll show you how we can derive this, but you should remember this. You get straightforward questions on this in mains, and people don't remember it. That's what I keep telling you. If you can just solve for this entire thing, like X-ray, Bohr theory, and everything, for each part, if you can solve 50 to 60 questions, X-rays itna nahi hoga. X-rays maybe you'll get 20, 30 questions. If you do that much, you will remember the stuff. And because these chapters being the last chapters, right, you won't write enough tests, and you will ignore because you will be busy with your revision. And then these things will become your big backlog. And last time you won't be able to cover up also. It will become too scary to look at these things because they're completely new. So don't ignore them. Spend some time and do finish your material. If you see in the group also, I sent you two things, Modern Physics 1 and Modern Physics 2 karke, if you observe. Those are actually Elenka booklets, right? The questions are very good. Zyada nahi hai. The thing I liked about them was like in everything, right? They have something total milake. I think they have around 250, 300 questions, I guess. 200 maybe. It's a good number. So if you try to do HCV, that is also good. But problem HCV, I think there are 4 chapters. It becomes little lengthy. So if you don't have time to do everything, you can just do the 2 things which I sent you. And they also have a good theory. You can read it, little history, little, more decent words and all. So just for terminology. So you can just follow those 2 things which I sent in the group. That will work. That is your atomic number of the target. So you can finish your classes ka material and you can finish off that. I think that should be sufficient for both. That will be a good amount of practice. Don't ignore this chapter. The B is the screening constant. So we can derive this 1 by lambda is Rydberg constant. 1 by n1 square by 1 by n2 square into z effective square. If you multiply c on both the sides, this will become c by lambda, which is frequency, is equal to rc 1 by n1 square by 1 by n2 square into z minus b whole square. If you put a root on both sides, you will get root frequency is equal to root over rc 1 by n1 square by 1 by n2 square into z minus b. There. Now, if you look at the formula, this thing looks like Moseley's law. Root frequency is equal to a into z minus b. So the Eka value is root over RC. So this Eka constant will depend on the electronic transition from which orbit to which orbit. That B is your screening constant. So for example, if you take for K alpha, you are jumping N1 is 1 and N2 is 2. Eka value will be root over 3RC by 4. And the Beta value is approximately 1. If you take K beta, then N1 is equal to 1 and N2 is equal to 3. Then here A will be 8 RC by 9. So that Eka value will depend on that. And Beta value, we don't know. They have to give this. We can't say it is 1 or 2. And if you try to plot a graph between root frequency and Z minus B, you can clearly see it is a line passing through the origin. We get lines passing through the origin. In this, can you tell me which is K alpha and which is K beta? So this is a straight line, right? Y is equal to mx. So A is the slope. You can clearly see K beta has more slope than K alpha. So that is K beta and this is K alpha. Clear with this? Because the slope value, slope tan theta is nothing but A. So it's a graph between root frequency and Z minus B. Clear with this? That is one. So that's your main theory. Like I said, there are only two formulas in X-rays, the Moseley's law and lambda minimum and the graph. So these are the three main things. The next thing, now this is removed from the mains portion, but it can be asked in bits or something else. Absorption of X-rays, not a big concept. If you guys remember, I taught you X-ray ka thing before in wave optics. Remember Bragg's law? Interference due to X-ray. So that also could have included here. This is valid for all other electromagnetic waves. So what this thing says is, if you have a slab and if you shine X-rays onto it, the initial intensity, as these X-rays pass through the material, they start getting absorbed. The intensity keeps decreasing, let the distance be X. The formula is given by I is equal to I naught into e power minus mu X. Where I is that's it, you just need to know that formula. Intensity of X-rays after traveling distance X. Mu is the absorption coefficient. So if you take lead, mu ka value is pretty high. If you take something like copper sheets, mu ka value is very less. So lead absorbs X-rays much better than copper sheets. That is the reason whenever you go through the airport security, right? If you put a lot of coins in your bag and go, they'll tell you to remove all the coins because the metal will start blocking it. That's the reason they ask you to remove your laptop also and charging cables and everything. because it's a bunch of metal, so it actually blocks the view for them. You put a book, nothing will happen. The X-rays will just pass through. So that's your formula. And if you actually observe this formula, doesn't this guy look like n is equal to n naught e power minus lambda t? Remember radioactivity? It looks like that. So here the half-life T half will be ln 2 by lambda. So this is the time when your number of atoms become half. So using the same logic here, I can also say x half, meaning this is the distance traveled for the intensity to become half, is ln 2 by mu. So this is the distance when the intensity of X-rays becomes half. So just like half-life, you can say half-life distance. But this much concept you should know. There is nothing more on this. They used to ask questions on this, but it is removed in the portion last year. So bits में तो अभी भी है, so just in case. They say they removed it, but they'll always ask. And if people cry and jump and shout, then they give bonus. Next thing, Compton effect. Yeah, again, another formula you need to remember. Basically, this is the scattering of X-ray. So sometimes what happens when this photon goes and hits an electron or a particle, it bounces off like an oblique collision. Because it has a particle nature, it happens. So scattering of X-ray photon with matter. More than the formula, right? Theoretically, this is important. Like they can ask a question of this sort: which of the following phenomena can explain particle nature of light? Photoelectric effect, Compton effect. So these things will explain particle nature of light. So if you have an electron, let's say we have a photon of lambda naught. So energy of this photon is hc by lambda naught. After collision, the electron bounces off at an angle. Let's say this angle is phi. In this process, you also get another photon, lambda dash, at an angle theta. This is the scattered photon. So the photon actually loses some part of the energy. Remember here nothing is getting absorbed. If you remember, we made a statement and photon has to be completely absorbed and not absorbed at all. This doesn't belong to that category. It is not getting absorbed or anything. It just gets scattered. And here the wavelength lambda dash will be greater than lambda because you lose energy. So the formula is given by lambda dash minus lambda, that is a change in wavelength, is h by mass of the electron speed of light into 1 minus cos theta. This can be proved with energy conservation and momentum. So that's fine. This is the wavelength after scattering. M is the mass of electron and c is the speed of light. There. That's your whole theory of X-rays. Let's see a few questions on this. That's a bit of a theory. Make sure to go through the whole thing. Let's get this. Remember, there are only two formulas, the lambda minimum and that Mosler's law. Let's see the first one. Electromagnetic waves of several hundred kilometers can exist. True, radio waves do exist. High energy gamma rays. Gamma rays are wavelengths lesser than X-rays. They travel at speed of light. Wrong. All electromagnetic waves travel with the same speed of light. X-rays transverse wave. Electromagnetic penetrant matter. True. 134. They do ask. 27. An X-ray tube with a copper target is found to be emitting wavelengths other than copper. So target में there are some impurities. The K alpha of copper is 1.5404 and the other two K alphas are 0.3851 and 1.6578. Identify the atomic number of the impurities. Think, take a minute, how will you approach that? So which formula we have to use? 27 के लिए? Root over frequency is A into Z minus B. Since you're talking about wavelengths, I can say root over C by lambda is A into Z minus B. B is 1 because it's at K alpha. So you can clearly see 1 by root lambda is proportional to Z minus 1. So I know copper and I need to find the other two guys. So I just need to apply the formula. So root over, let's call this thing as lambda 1 by lambda copper will be Z copper minus 1 by Z1 minus 1. So lambda 1 is 0.3851 by 1.5404. Z copper is 29, that will be 28 by Z1 minus 1. This thing actually is 1 by 2. 28 by Z1 minus 1. So then will be Z1 will be 56, 57. Then you just have to put the formula and keep solving. And similarly for the other guy will be root over lambda 2 by lambda copper. Same story, Z copper minus 1 by Z2 minus 1. So lambda 2 will be 1.6578 by, I'm not sure how will you solve that though. This is 28 by Z2 minus 1. I will get Z2 from here, I'll leave it to you. There, Moseley's law. You just put in the formula, you get the answer. 28. This thing I just showed you in an example. This one, isn't it? This was the slope. So 1 by lambda was R into this will be root frequency, which is root C by lambda. Root over RC 1 by N1 square by N2 square. You should know your derivation. That is your slope. For K alpha, it will be root 3 RC by 4. K beta root over 8 RC by 9. Divide them, you'll get the ratio. That is your 28. Clear with this? Let's do one more. Let's see. Again, same thing.
But what about the...
So this will be root frequency. Again, he's talking about wavelength. So root over C by lambda is A into Z minus B. So we don't know what is that impurity. So root over lambda 1 by lambda 2 will be Z2 minus 1 by Z1 minus 1. Numbers are given good. So this is 225. 500 and Z2 is what we need to find, and Z1 is 27 minus 1. That is 15 by 10, 1.5 into 26. That is 13.3. Z2 is 40. Clear this? Yeah. Straightforward substitution. Let's get this. K alpha and K beta X-rays are given. Find the energy of L alpha. Here's an easy one. Yeah. So what is K alpha? If you think about this, L alpha is nothing but transition from. So L alpha is simply n is equal to 3 to n is equal to 2 transition. And K alpha is this. So you simply need to fit that difference in energy. So energy of an L alpha photon is nothing but energy of a K beta photon minus energy of a K alpha photon. Agreed? So 3 to 1 minus 2 to 1 will give you 3 to 2 ka transition. This is 3 to 1 transition and this is 2 to 1 transition. That will give you the difference between 3 to 2 transition. The energy difference. And what is the energy there? 12400 by 1 angstrom minus 12400 by 2 angstroms. That thing will end up with yeah, half of this, 6,000. We gave 12420. 6,210. That's your energy of L alpha. Clear with this? There, if you see the questions are not tough, they're all like this only. Okay, with that, we'll wrap up for the day. So next class, when we catch up on Thursday, we'll continue from here. You will see few more models of X-rays. It's not much left. Maybe we'll do another 3 or 4 problems, and then we'll go ahead with radioactivity and nuclear physics. We will wrap up the chapter next Friday. Next Tuesday, we don't have a class because of Diwali, but next Friday again, next Thursday, I mean. Next Thursday, we will wrap up the chapter. It should be done. And then after that, we are left with semiconductors and stuff. Okay, with that, we'll wrap up for that day. So do start solving. You can finish off till X-rays, right? Don't wait for the whole thing to get over. It'll become too much then. So there is a test also online this week till Thursday night. So make sure to give. And Saturday also we have a session. So do make sure to attend. So, any doubts, anything else, please stay back and ask, or else I'll see you on Thursday.